Hey guys, welcome back to another RASK Maths tutorial, and in this tutorial I'm going to be showing you guys how we can actually determine the angle which a rotation matrix is actually trying to rotate something by. So if you don't know, the 2x2 rotation matrix is basically given as r of theta is cos theta, sine theta, minus sine theta, and cos theta. This basically allows you to create a matrix which will rotate any point in 2D space. It rotates it by any angle so that we can actually transpose it, I guess. Not transpose, rotate it by any angle so that we can just rotate it around the origin. And usually you want to rotate points, right? But what happens when you're given a rotation matrix and the question's asking you to find theta? And this might seem easy, right? Like, let's say I just give you the rotation matrix minus 0.8, minus 0.6, 0.6, and minus 0.8. So if we use identities, we know that this has to be identical to the original rotation matrix, cos theta, sine theta, minus sine theta, and cos theta. And then from here, it might seem trivial. We can just match up the individual items, individual elements, and find theta from there. So let's just say we match up minus 0.8 cos theta as well as these. Well, let's just do this one first. So this is going to give us cos theta equals minus 0.8. And so theta has to be arc cos of minus 0.8, which is, let me just determine this using a calculator. It's just going to be about 143, right? Well, this is actually wrong. And you see, if I put my 143 into sine of theta, we're not going to get minus 0.6. Sine of 143 is actually going to give us positive 0.6. Is equal to positive 0.6, and it's not equal to negative 0.6 like it should be. So why is this? Well, it's because, remember what a cos graph looks like. It's something like this, and we're essentially trying to solve it as minus 0.8, so that's here. And we've got this first solution. This is 143. But remember, there's actually another solution, 360 minus 143. And this is going to be about 217. And so let's try this new solution, because both of these are going to give us cos theta equals 0.8. So we've dealt with both of these. And once we deal with one of the sine cases, the other one is also going to deal with itself, because it's just a negative of each other. So we're basically just trying to match up this cos theta and sine theta and find this theta which satisfies both of them, not just one of them. So if we take theta to now be 217, then sine of 217 degrees, well, this is actually in fact going to be minus 0.6. And so we found the right answer. Theta equals 217 degrees, or a rotation of 217 degrees anti-clockwise, also known as 120, about 143 degrees clockwise, I believe. That's essentially what we get. But how would we do that if we didn't want to have to mess with all of these signs? Like, just messing with these signs, it can get a bit confusing, especially if you're in an exam. Well, what we need to remember is a rotation matrix. If we just look at the I hat of the rotation matrix, this is just going to be, sorry, I should probably have drawn this a bit better. So I hat is going to be somewhere over here, minus 0.8 and 0.6. And remember, we don't actually have to care about j hat because it's always dependent on I hat. It's just going to be a 90-degree angle. So we can just worry about this I hat here, because j hat is just dependent on I hat anyway. It's just 90 degrees out like this. So I hat shows us the angle it's been rotated by, and it is actually that angle there. And I think you'll notice what we can do is, if we call this angle theta, well, our first initial value of theta was actually 143 degrees, and we saw that that didn't work. So, oh, sorry, I just realized I've drawn this wrong. That explains why it was a bit messy. This should actually be pointing over here. Alright, so this I hat is pointing to minus 0.8, minus 0.6, and the angle theta it's rotated by, remember the initial I hat is just pointing straight to the right, so this is the angle it's been rotated by. And the way we actually need to think about this is, if we imagine this as a unit circle, like so, I know this is a horrible circle, but bear with me. So imagine this is a unit circle. We can't just look at the sine components. Remember, sine of a unit circle is the height. We can't just look at either the sine or cos, because if we just look at the sine or cos, well, it could be here or it could be here. Both of these would give the same sine and cos of these angles, right? So if we look at the cos, this distance out here, we could have this. So we could have this angle, but we could also have, if it was over here, we could also simply just have something like this, where this theta would also give the same cos. So we can't just look at the sine and cos. You might be thinking we can look at the tan, because if we tan, so if we were to like take this sine and cos, put them over each other to get tan theta equals minus 0.6 over minus 0.8, or tan theta is 3/4. You might think by combining these we could get some kind of uniqueness, and then we could find tan and then find theta using that. But again, theta represents the gradient, right? Because if we have a point here, we know this is sine, this is cos. We know tan is sine over cos, so therefore the tan just represents the gradient of the radius of the unit circle. And so there's multiple values for which tan theta are going to give the same point. It's either this is going to give the same value as this, since both of these have the same gradient. So instead, what we need to do is make use of an identity. And this identity specifically is going to be tan of theta over 2 is equal to sine of theta over 1 plus cos of theta. And let's have a look on a unit circle to see how we can actually prove this identity. So this is the unit circle of radius 1. Let's just pick a random point. And yeah, so we can know that this length is going to be sine of theta, and this length is going to be cos of theta. Now what I'm going to do is draw in an additional triangle, sort of here, like that. And we know this angle here is going to be 180 minus theta. And then therefore, since these two lines are identical, the remaining two angles have to be split as just theta. These two angles are the same since it's an isosceles triangle, and so this angle has to be theta over 2. Now, if we look at this triangle here, we can see that, let me just make this triangle a bit clearer. If we look at this triangle here, we can see tan of theta over 2 must be equal to, well, opposite over adjacent, so sine theta over cos theta plus this bit here, 1 plus cos theta. And there we go, we've proved it. You can also prove this using the double angle identity by just doing something like this is equal to 2 times sine of theta over 2 times cos of theta over 2, and then this is again just double angle identity in reverse. So this is equivalent to 2 times cos squared of theta over 2. And then you can see these coses cancel, these 2's cancel, and we just end up with using tan theta equals sine over cos, which is sine theta over 2 over cos theta over 2, which is true. So this identity is definitely true. And what it actually corresponds to is the fact that, well, this tan represents the gradient of this line, right? I'll just make it clear. This is representing the gradient of this line, tan of this angle. So what you'll notice is as this point varies, this point can represent any I hat of the rotation matrix. And you'll see as this point varies across the circle, the gradient of this line is unique to every single possible point on this circle. Whereas the gradient of this tan line was not unique, since if it was over here, the gradient of this I hat is going to be the same as the gradient of this I hat. So the tan from the center doesn't actually have a unique correspondence, whereas the tan from one of the edges, this actually has a unique correspondence to every single possible position I hat can take on the graph. And therefore, there's a bijection between the possible values of I hat, this, and the possible values of tan theta over 2. And therefore, if we just use this identity, so let's remember our initial thing. We know I hat dash is just going to be it's just cos theta over sine theta. Just taking the I hat component of this since we're ignoring the j hat. And we knew that that was equal to minus 0.8 over minus 0.6. We know there is a 1-to-1 correspondence between possible I hat values, or I hat dash, as you want to see it, and the value of tan theta over 2. This. Another way you can see it is, well, this is essentially saying this equation we can rewrite in terms of theta to just be theta equals 2 times the arctan of sine theta over 1 plus cos theta. Now remember, arctan has its range from minus 90 degrees to positive 90 degrees. And so there's no way we can use just this formula on its own. Like if we were to try and work out tan on its own, there's no way this would give us a unique angle, since this angle can range from 0 to 360 or 180 to minus 180. And this only has a domain of 180 degrees, whereas we need to have a domain of 360 to account for all possible angles. So that's where this 2 comes in, because now, with the help of this 2, this now ranges all the way from minus 180 to positive 180, thus giving us all the possible values of theta we could get. And therefore you can see this is going to give us the easiest way to calculate theta given the identity. So all that comes down to is, to use this formula, we just set theta equals 2 times the arctan of sine theta, which we know has to be minus 0.6 over 1 plus cos theta, which is just going to be 0.2. And putting this into the calculator, let's see what we get. So 2 times arctan of minus 0.6 over 0.2, and we do get minus 143 degrees. So if we look at the original rotation, this is equivalent to rotating it this way, minus 143 degrees. And yeah, so this is the formula you need to remember. Just plug in the values for sine and cos theta from the rotation matrix into this formula, and your answer should pop out without any need of you messing around with the signs or primary and secondary values of cos and sine theta. So thanks for watching, and I'll see you guys in a future tutorial. Bye.